Okay, so in yesterday's class we looked at series and parallel resonant networks. I hope you folks had the time to go back and work out the expressions for Q based on the physical definition d phi by d omega, etc. If not, please do it today. Okay, please do it over the weekend. Basically, we saw several definitions of quality factor for any network. Okay, you can start from the physical definition, which is either peak energy stored by energy dissipated per cycle, or omega times peak energy stored by power lost, power dissipated in the resistor, in cycle, etc. Okay, so there are also other, that is a physical definition. There are also definitions based on networks. Okay, so if your network, electrical network has an impedance Z, the imaginary part of Z over the real part of Z will give you the quality factor. The quality factor can also be seen as R over the characteristic, not root of L by C of the resonant network. It can also be seen as minus d phi by d omega. Okay, the slope of the phase characteristic of the impedance. And finally, system level definition. You can relate, because Q is also related to the bandwidth, okay, of the system. You can also talk about omega naught by bandwidth. Okay, when I say omega naught by bandwidth, it's you find out the 3 dB bandwidth of the system. Okay, you'll have a 3 dB bandwidth on the left side, 3 dB bandwidth on the right side. The distance between those two is delta omega. So that is in fact the way it has been defined. Okay. And finally, towards the end of the previous class, we pointed out that the there are networks which are neither purely series resonant networks or parallel resonant networks. And what we said was, over a narrow band of frequencies, we can actually transform from one type of network to the other type of network. And we actually found out the transformation equations. And what we found was, if you take a series, R and C, it can be converted into a parallel R and C over a narrow band of frequencies. The parallel R and C are actually frequency dependent quantities. However, at the frequency of interest, once the frequency, you now get fixed values for the parallel values. The parallel values of R, L and C were derived. So the parallel value of the resistance is R into series resistance into 1 plus Q squared. The parallel value of the inductance is series inductance into 1 plus Q squared over Q squared. And the parallel value of capacitance is the series value C into Q squared by 1 plus Q squared. So the resistance value increases by quite a bit, 1 plus Q squared times. The capacitance value is slightly smaller. The inductance value is slightly larger. Okay, that is the quick summary. We decided to write it in the form of Q because very often the Q of the network is of interest to us. The reason is very simple. So towards the end, we kind of stopped 1 minute. Yeah, stopped right here, where we said this network is actually an impedance matching network, because it can actually take a series resistance, convert it into a parallel resistance, make it look much larger if you were to resonate out the imaginary part. Okay. So you can now transform from one to the other. Now please realize that the transformation will be calculated at some particular frequency. Okay, having said that, around that frequency the transformation will be more or less valid. Okay, as you move further away from that frequency, the transformation will start deviating. Okay, so that is where Q comes in. Okay, the quality factor will now depend on, or will now decide how wideband or narrowband the circuit is going to be. The impedance match is going to be. Okay, if you have an impedance matching network with very low Q, okay, it means that it is going to be a network. If you have an impedance matching network with high Q, it is going to be a narrowband matching network. That is where matching matters to us. Okay. Make sense? Okay. Now, so let us now start looking at these networks. So we have come up with a prototype network. So the network that we came up with was this, I believe, yesterday. Sorry, I redrew it in a very specific form. Okay. And I said, if I take this network and look, okay, so the matching network itself is this portion, and Rn was R into 1 plus. That Rn is always larger than R. Okay, does that make sense? Rn is always larger than R because Q squared is always a positive number. So this is one matching network that converts from smaller resistances to larger resistances. If I took the same network, flipped it around, okay, what is Rn prime? Huh? I now build a network where I have Rp, okay, in parallel with the inductor, and then you have C in series. So I have just taken the original network, flipped it around, I am putting a resistance Rp across the inductor. Rp by 1 plus Q squared. Does it make sense? If I took the exact same values, I'll just get R. I took the exact same values of L and C, and I put in R in as the load, I will get R, because these networks are completely reciprocal. Okay? So now, if I flip the network, I actually am able to reduce resistance. So now I have found a very, very simple matching network which can go reduce impedance downwards or upwards. This is exactly what I want to start, what I started off desiring to do, because I want to match some arbitrary impedance to 50 ohms. Okay. At every time there is an interface between the integrated circuit or my active circuit and some off-chip component. That off-chip component could be the antenna, could be a filter, could be just be a transmission line, we do not know. Those are all standardized at 50 ohms. You do not have the option of making the off-chip component at some other impedance. The reason is very simple, that off-chip component is normally made by somebody else, not being made by you. Okay? Excellent. So now let us, first before we start, I'll work out an example, but before we work out an example, are these the only circuits possible? Or are there other circuits that can do this? It turns out that there are several different circuits that can do this. First of all, if you just look at these circuits, we started off with a series R and C and put an L in parallel, right? We could actually have started off with this network also. We know that a series R and L can be, so I'll call this R, L and C. I could have started off with this, and I could have transformed this over a narrow band of frequencies into a parallel L and R. Okay, I generated out C and LP and then match the network. What is this R value? What is R in here? It is again R into 1 plus Q squared. The expression for RP is the same. The only difference is how you calculate Q, right? In the series RC case, you calculated the Q as 1 over omega CR. Okay, here you calculate it as omega L by R. Okay, so remember that, this should be RP. Okay. So in all these places, in all these networks, the value of Q is different. It depends on the magnetic or the capacitive components that you choose. Okay. What is the difference between these two networks? So these are the two matching networks that we have. In fact, we have 4 of them, right? We can flip them around, go down in impedance also. What is the difference between these two networks? Which one? The upper one will block lower frequencies. The lower one will block higher frequencies. Okay. So the upper one is a low pass network. Okay. The lower one is, the upper one is a high pass network. The lower one is a low pass network. Right. So depending on the frequency response, out of band frequency response, you would choose one of these. Okay. Maybe you are interested in harmonic content. You are interested in suppressing harmonic content, in which case you will want a low pass network. Maybe your amplifier is nonlinear. It is putting out second, third harmonics, okay, at the output of the power amplifier, for example. I want to make sure they don't exist. I may use a low pass network. Okay. Maybe I need to block DC. Okay. So I may choose the high pass network which has the series capacitance. I don't want to add an extra blocking capacitor. This blocking capacitor is good enough. DC blocking capacitor. Okay. So there are indeed many constraints over based on which you would choose the type of network. Another constraint are the values of L and C. If you decide to build these two networks, the values of L and C that you get will be different for the two networks. Choose a low pass network or a high pass network. Okay, and in general, the inductance is the one that will occupy a lot of area. If one of them gives you 2 nanohenry, the other one gives you 100 picohenry, you would probably try to choose the one with 100 picohenry. You expect it to be a much smaller inductor. Okay, so like I said, there are many different constraints based on use. Okay, let us come back to this. So suppose, let us say, work out a quick example, right, so that you will understand what we need to do and why. So first step, what kind of specifications do you expect to be set for this matching network? So the first thing you need to know, R values, right? You need to know what you are transforming from 50 ohms to something else, 50 ohms, 100 ohms to 200 ohms, etc. Right? So what you need to know? You need to know Rn and RL. Right? Okay. What else? Frequency of operation, omega or F. Okay. What else? That's all. So, let us work out an example. Let us choose some values of Rn, RL and omega and figure out whether we need more constraints or not. Okay, so let us say I want to change from 50 ohms to 200 ohms. We work out an example. Let us say 1 gigahertz. Okay. So you have to choose any one of these networks. So let us choose the second one that we work with. Okay. What do I calculate? I have to calculate the values of L and C. Okay. How do I do this? Where do I start? Q. Find out the Q. Because you know that Rn, so you know that you are going to convert this into a parallel RLC with some RP, okay, which is going to have some RN. That has to have a value of RP resonance, okay. So you know that RP is 200 ohms and RL was 50 ohms, right? And what is the value of RP in terms of RL? It is R into 1 plus Q squared. So the first thing you can find in these types of networks is the Q. And as you can see, in this case for these networks, the value of Q is not set independently. It is set by the ratio of Rn and R. Okay. So in fact, I'll call it, in general, the value of Q is root of Rp by Rs minus 1. Okay. What this is also telling you is that instead of going to 200, if you're going from 200 to 800, the value of Q would be the same. Okay. That's what this is telling you. So the ratio of resistances is setting the Q and not the actual values. The corollary of this is that the bandwidth of match is not set independently for this network. Okay. So these types of networks are called L match networks because of their shape. Okay. You have a shunt component and a series component. Okay. And for L match networks, you actually have two components, an L and a C. Okay. So you only have 2 degrees of freedom for your design, and those two will be used to set the ratio of Rn and RL, okay, and the frequency of operation. Okay. You cannot constrain the system any further. For example, in terms of Q. Let us come back to this. How do you go about calculating this value? So what is the value of Q in this case? In this case it is root 3. Okay, so this is 1.73. In general, this is a moderate value of Q. It's on the lower side for sure. Okay. What do you do next? So now that you know Q, okay, you can calculate, because you know RP, Q, you can calculate the value of C and LP. You can also calculate the value of L. You don't even need to calculate LP. Okay, because you know that Q is omega C RP. Okay, this gives you the value of C. Because you know RP, you know omega, you know Q. Similarly, this resonant network, it is omega L by RL. You know RL, you know Q, you know omega. So this will give you the value of L. Can you please quickly calculate these values for our system? C, what is the value of C? So 8.6 picofarad. Okay, what is the value of L? 86.9 nanohenries. Is that right? Okay. 86.6. Is this correct? Is everybody getting this? Can you please cross check your result? Okay. Okay. So, first step, 86.6 nanohenries is impossible to realize, okay, on an integrated circuit. It's just too large, first of all. The second problem is that even if you were to realize such an inductor, whether it's on an integrated circuit or outside using some other technology, at 1 gigahertz, such an inductor will not behave in an inductive fashion at all. Okay, because every inductance will have its own capacitive parasitic, at which you will have something called, based on which you will have something called self-resonance. Both inductors and capacitors will have a self-resonance frequency, where they will resonate their own respective capacitive or inductive parasitics. Does that make sense? Beyond the self-resonant frequency, the capacitor will look inductive and an inductor will look capacitive. Okay? So, an 86.6 nanohenry inductance is just, you would just not go with this design, this particular design. So now you'll have to look at the other type of matching network. So let us do the same calculation for this matching network. So please calculate the same values for this. Q stays the same. Okay. So please calculate the values of C and R, C and L in this case. Are these correct? Values are correct? Okay. So now these are much better, right? The capacitance is smaller, the inductance is much smaller, okay, and 18 nanohenry again is too large to be built on the chip typically, but off chip you can probably get 20 nanohenry inductors, okay, which will most at 1 gigahertz, okay. So obviously, so Mn2 is better, right, for us, or more realizable. So that should be your choice, if you had a choice between these two. Any questions? Yes. Omega equals 1 by root L. So you have omega equals 1 over root LCP. Yes, of course you can. Okay. And then, so okay, this is true. You can use this, but what does that give you? It will give you the value of Cp probably. And then you can calculate C as Cp into 1 plus Q squared by Q squared. You can do that. That's a little bit more roundabout, right? That's all. So I just directly calculated based on the individual components. Any questions? Okay. Yeah. The previous one. Case 1. Okay. But when I asked, everybody else agreed with this number. Okay, tell me the number. Okay. 1.7? Well, that changes really, right? This one has the smaller inductance. Okay. So 13 inductance is on the edge of what you can, probably 10 nanohenry is typically what you can realize, without using too much area. Okay. So now this changes. So now I have to say that the first matching network is better. Okay. In terms of area, but because the values are so similar, you may actually choose the second one if you want a DC blocking cap. The reason is very simple. Imagine this circuit anyway requires a DC blocking cap. Okay. If I use matching network number 1, I'll again have to put an extra DC blocking cap either on this side or on this side. Right? Going to be much larger probably. If you're going to do that, you may be better off just choosing matching network number 2 if that is your constraint. Okay. So like I said, there are several different constraints. Okay. Any other questions? Okay. How many different types of L matches are? 4 different types of L matches. They are up matching, down matching, okay, low pass, high pass. Okay. So you have 4 different types of L matches. Okay. Now, of course, as we started off right at the beginning when we started this example, I pointed out that the number of constraints that you can set are purely the ratio of the impedances and the frequency of operation. Now imagine you want to set the bandwidth, so in other words the Q of the match independent of the Rn and Rl or Rn over Rl, right? So you will need to move to a more complicated matching network. Okay. So you need to add a third component. Okay. So you need to move to what is called a pi match. or a T match. Okay. So why do I call it a pi and a T match? Very simple. Okay. Let me take any one of these guys, and I start with this guy. I want to add a third component. Okay. I can add it in two ways. Okay. Let us say this was C and L. Okay. One way is to add a series component to the left of the capacitor. So this would be C, and I'll call this L1 and L2. So I basically add a component here. That will create something called a T match. Okay, that is because the shape is a T. I can also choose to add something in shunt at the right side. So something here. Okay, that will create a pi match. If I were to do that, so this is the T match, this is the pi match. Okay, and effectively you will see that both these structures can be obtained by cascading matches. Okay, so I could cascade this with this, okay, to get the T match. Okay, so this is the low pass version. I could cascade the the other way, the same low pass version, the other way to give you the pi match. Okay. How many different types of pi matches are there? There are two different types of pi matches. One is the low pass pi match, the other is the okay. So I could have for the pi match, I could have this, or okay. Similarly for the T match, the shunt component could be an inductor. Okay. And now this pi or T match has 3 degrees of freedom. Okay, because I have now added a third component. Does that make sense? So I should technically be able to set the quality factor of the match also independent, okay, of the independent of RL by RM. Okay, let us take any one of these, and let me take the pi match, and let's figure out how to analyze this first. So let me take one of these. Okay, remember that it is the cascade of two L matches. So right off the bat, I'm going to draw it in that fashion. Okay, even though the final pi match will be realized with one single inductor, I am actually going to draw it in that fashion for analysis, and you will see why also in just a moment. If you are able to find out the independent, the values of L1 and L2 independently, plus L2 will give you L. So the internal node that I have pulled out is just hypothetical. Okay, just purely for analysis. If you were to build this, you would only use 3 components. You would not use 4 components. Okay. Very good. So now, actually before we go, because this relates to the point we are about to tackle. Suppose I go to one of these L matches, any one of these. Let's take this guy that we have just designed. Okay. Okay. If you use ideal L and C to build this match, please note that the impedance looks like Rn for your driving circuit, but the power dissipation happens only in RL. With ideal L and C, there is no power dissipation in the matching network itself. So normally the matching network is expected to have very little loss. Okay, so that is first thing to remember. Okay, if that were the case, okay, let's assume you know that ideal L and C does not dissipate any power, right? Which means power delivered by your source to Rin should be equal to power dissipated in RL. What does that mean for us? So for example, in our case, Rn is 200, RL is 50. What does that mean for us? For the voltages across Rn and RL? So since the impedance level is lower, right, the voltage across RL should also be lower. You understand? So first thing, if you just purely look at the swings at these nodes and these nodes, they are going to be different. How different are they going to be? It depends on the ratio of the resistors. It depends on the quality factor of the network in this case. And how does it come about? It comes about because if you remember in yesterday's class, we calculated that at resistance, the voltage across the inductor and capacitor is going to be Q times the voltage across the resistive component. Okay, so effectively you are using these impedance matching networks not only for impedance matching, but to also get passive voltage gain or loss, as the case may be. Okay, if you were to flip it the other way, in other words, if drive a lower impedance and transform it up to 50 ohms, you are getting a passive gain, passive, lossless, noiseless voltage gain. You are using only L's and C's. As you know from the analog ICs class, L's and C's do not produce noise. Okay, so this is as ideal as you can get. Okay, if you have ideal L's and C's, you can indeed get higher voltages without any power loss, without any added noise. Okay, you cannot get power gain. Same as the analog circuits course, as you learned in the analog circuits course, you can use transformers to get voltage gain. You cannot get power gain out of it. Okay, same thing is valid here. In fact, what we did not discuss, we could have started off discussing this. You can use a transformer for impedance matching. I did not cover it because I think all of you have studied it. You may not tie it to the impedance matching concept, but please remember that if you have a transformer with a 1:n ratio, the impedance goes as the ratio of n squared, because the voltage and current get transformed by n and 1 by n. Okay, the impedance will get transformed by n squared factor, depending on which side you look at. Okay, so wanted to build an impedance matching network, okay, from 50 to 200, you can use a 1:2 transformer if you want to get 50 to 200, and that is also commonly done. Okay. Okay, coming back to this, the reason I brought it up is because that is very important in the analysis of this pi match network or T match network. Okay. So first step you have to remember is that there is no power dissipated in either L1, C2, L2. So the power dissipated in, power delivered to the network is what is delivered to the load. Okay. Now what that matters, what that means for us, is that, see, first of all, the quality factor of the network decides the relative value of the resistive to reactive component. If your quality factor was infinity for any network, that means there is no resistive component. For this network, okay, since there is a quality factor that we have derived for these matching networks, which is purely derived based on RL and the values of L and C. Okay, and therefore, because you are now splitting this matching network into two L matches, I am now going to, just like we said, power delivered to RL is same power is delivered to Rn. I am now going to define an intermediate impedance, I'll call it Ri. Okay, you can now conceptually think of Ri as being the load for the first L match network. Any power delivered at the input is being delivered to Ri. For the second L match network, any power delivered to Ri is actually being delivered to RL. Does that make sense to everybody? Okay. If you start this, right, you can show, okay, I'll put up a small note. If the calculation is like a one-page quick calculation, you can now show that, so let us say this was Rn and let us say this was RL. Okay, so I'll redraw that here. So this was RL, C2, C1, L1, L2. This is Rn. So this is Ri. Okay. You can show that what are the respective Qs of the two networks. So you can now define a QL and a QR, the Q of the left hand network and the Q of the right hand network. What is QL? Is Rn being transformed down or being transformed up? Look at it from the other side. Let us look at QR, since you actually have a resistor there. What is the value of QR? So you will take RL and C2 parallel combination, you would convert to series combination. When you go from parallel to series, what happens to the value of resistance? It goes down. Okay, so, right, and you expect Ri to be less than RL. That makes sense, right? What about QL? It's the same thing. Conceptually, these are all reciprocal networks. You can load Rn at the input and look at the impedance looking leftwards from the intermediate of the circuit, from the center portion. Again, you will find that QL is root of Rn by Ri minus 1 and Ri is less than Rn also. Okay, so actually this intermediate impedance for the pi match is going to be both the load impedance as well as the source impedance that you are trying to match to. Now the power dissipation factor comes in because you can now show that the overall Q of the network is simply QL plus QR. It is just the sum of the two Qs. The overall Q of the pi match of the two cascaded L matches is simply the sum of the left hand side Q and the right hand side Q. Okay. For now, you just take it as given. I'll upload the proof as a simple calculation. Yes. if your cascade of circuits is magnetic, right, you can probably derive, I don't know that anybody has derived it, but I am pretty sure you can derive the sum of the overall Q being equal to the sum of the cascaded Qs. Okay, it is definitely possible. Okay, so now you can see that you have now introduced, at least conceptually, a third variable Ri apart from Rn and RL, which is going to help you set the quality factor of the network, of the matching network. Does it make sense? So, original L match, it was just root of Rn by RL minus 1, right? Or root of RL by RL minus 1, depending on whether you're doing series to parallel or parallel to series. In this case, you now have an additional term Ri. Okay? So, now, what can you tell me about this Ri relative to the value of the Q? As Q increases, to build a very, very high Q matching network, you can see that your Ri is going to be extremely small. I hope you see that. Right? As the Q starts becoming smaller and smaller, okay, Ri will start approaching one of the impedances, the lower of the impedances. Make sense? And once it hits that lower impedance, you cannot get any lower Q than that. Does that make sense? And Ri is just hypothetical, it's just conceptual. Okay. Now how will you approach the matching problem? Now it should be extremely simple, isn't it? You now have a Q specification. Okay. You are going to calculate the value of Ri from that Q specification. Right? That is just a matter of solving this equation. Okay. You will end up with some kind of quadratic, right? If you square and maybe square a couple of times, you will find out the value of Ri from this equation. Okay? Because you know Q, Rn and RL, these are specified by your design constraints. Once you get the value of Ri, it is just a matter of designing two L matches. The left side L match and the right side L match. Because for each of these, you know the load impedance, you just need to find, and the frequency of operation. Okay, you just need to find out the value of Ri. Does that make sense? Will you be able to do this? Or do you want me to work out an example in the next class? Do you want me to work out an example, or is it pretty clear? Okay, since I'm not hearing anything, I will assume that the procedure is clear and move on. Right? If that changes at any time, just let me know. Okay? Fine. I'll just write down the last point. As I mentioned a little bit earlier, you can also match transformer matching is also possible, okay, as a matching network. Transformer can be used as a matching network also. Okay, I'll just write it down in the notes just for future reference. Okay. Okay, so we'll stop here. In the next, we will look at apart from the transformer, there is one other or two other types of matching networks, which are similar to the transformer but not exactly the same. They are similar to the pi network, not exactly the same. Okay, we will look at that in the next class. Okay, but before we go, sorry, I just realized I forgot to mention one thing, because we looked at the pi network, we did not look at the T network, right? What do you think will happen for the T network? It will just take a minute to make that point. In the T network, you will split the network in this fashion. You will again have an Ri. So maybe I'll call that RT. Okay. This is RL, this is RM. What do you think will happen? Yeah. So in the case of the T match, the intermediate impedance will be greater than RN and RL. Okay. Therefore, the expression for Q will correspond. It will be root of RT by RL minus 1 plus root of RT by RN minus 1. It's the other way around. This is QR. This is QL. Okay. Again, same condition. As you can see, larger the Q, larger will be the value of RT. Okay. As the Q becomes smaller and smaller, RT will start approaching the one of the impedances. It cannot go lower than that. With that, I'll stop here. In the next class, we'll quickly look at those two matches and other topics.